As we've been looking at power series, I've mentioned that you can think of a power series as a function. And you can think of the interval of convergence as the domain of that function. Those are the x values that when you plug them into that power series, the power series adds up to something. That would be your output. That would be your range of your function. Now it turns out that that function is differentiable, right? We know intuitively how you might differentiate it, and it turns out that the way you would guess is actually true. But we do need this as a theorem because our rules of differentiation apply only to finite sums. It's an infinite sum. But that's what this theorem, term-by-term differentiation theorem, is getting at. So they're saying, suppose you have a power series, and they're just saying non-trivial interval of convergence. So our radius is something other than 0. It's has some radius of convergence. It could be infinite, which would be great. Then you have some function with some domain there. And it turns out that that function is differentiable. And you just differentiate it like you would differentiate a polynomial. It's all just a big bunch of power rule, right? And that's what we're seeing here. That n's coming down, and then we're lowering the power by 1. So starting with a power series, you can generate the derivative of that power series by just differentiating the terms individually. This will be useful for us later on when we start looking at Taylor series and we want to find series for derivatives of functions. So let's look at an example, something simple. One of the first things we started with was this power series where let's say f of x is the series of just x to the n. That was like our simplest power series. It was centered at 0. All the coefficients were 1. But because it was so simple, it had the added property of being actually a geometric series. That power series is geometric. And so we noticed that because it's geometric, it converges to a over 1 minus r, and the first term in this is 1, and the radius was x. Not the radius, the common ratio. The radius, we know that geometric series converge when that r is less than 1 in absolute value, right? So we have this function. So let's return to the theorem. What the theorem says is not only can you view this as a function with inputs and outputs, right? Every time you plug in an x here, you get an output as long as we're in this range, right? As long as we're in x is less than 1. But also, that function's differentiable. If you could graph all those inputs and outputs, they would form a nice differentiable curve. So how would we differentiate that? Well, we could just do it symbolically. So the derivative, and I'm going to leave this lower index blank for just a second so we can talk about that. So the n would come down, and it lowers the power by 1, right? That's power rule. But because the added bonus we get here with this example is not only do we know this is the derivative, we also know it must be equal to the derivative of that, which would be 1 over 1 minus x squared. And notice it says that we're differentiable over the entire interval of convergence there. So we know that this thing also exists for all x less than 1 in absolute value. So not only is it differentiable, it's differentiable everywhere on that domain, or on that at least open interval there. Now the reason I left this blank is usually, if you notice over here in the theorem, for the derivative, n starts at 1. And that's just because if we start n at 0, there's not really a term there, right? So we just usually start it at 1 because that really is the first non-zero term in that. Let's also write this out long ways just so we can see what happened here. So we started off with the function f of x. That was, if we write that out, it's 1 plus x squared plus x cubed plus x to the 4th, and so on. And all the theorem is saying, Well, and we know this thing converges or has a domain, converges to 1 over 1 minus x, so long as x is less than 1 in absolute value. All the theorem is saying is that if you wanted the derivative of this function that's defined as a power series, its derivative is just, well, derivative of 1 is 0, derivative of x is 1, derivative of x squared is 2x, 3x squared, 4x cubed, and so on. And that would be equal to 1 over 1 minus x squared. And again, we inherit that domain there of absolute value of x less than 1. So what you would guess you could do, you can do. You can differentiate a series by just going through each term and taking the derivative there. That's all this is saying here symbolically. And it's differentiable over the entire domain, which is nice. Now, typically, we'll use this for situations where we've come up with a series for a function, and this will allow us to come up with a series for the derivative of that function when we start looking at transcendentals like sine x, cosine x, and others. This fact will be useful. We'll also see that this process goes the other way as well. If you have a power series, you can integrate a power series going term by term. So we'll look at that next.